My name is Paweł Stabla and I'm from Wrocław University of Science and Technology. I would like to present my topic, the mechanical investigation of filament wound composite cylinders subjected to axial compression. So at the beginning, I would like to say something about the filament winding technology and the mosaic pattern, which is one of the technological parameter involved in filament winding technology. So during winding, we have the stroke forward and backward, where when the bundle is deposited onto the rotating mandrel and going back, which is shown on the figure. In first circuit, we have only forward and backward stroke, so we can see that the fibers are interlacing. In the second circuit, you can also see that the additional layers are going one by now next to another one, and when there is the backward stroke, the mosaic pattern is generated. The whole mosaic pattern idea is shown on the lower graphs, which you can see different mosaic patterns. In this case, we have the patterns 1 by 1, 2 by 1, and 3 by 1, and you can see that there's a different material angle distribution, which gives different mechanical parameters, which might give different mechanical parameters. And the mosaic pattern is widely disregarded during research. It is not widely taken into account. The main factors which are taken into account during filament winding is, of course, the winding angle, the winding sequence, the different layers with different angles, and of course the thickness of the layer. So in this research, we've manufactured one layered composite filament wound cylinders. We use the chrome steel mandrel, which we covered with the adhesive wax for the better demolding, and the filament wound composite fiber reinforced plastic were wound onto the mandrel. At all, we produced 9 configurations with 3 different mosaic patterns and 3 different winding angles to see if the mosaic pattern, if the influence of the mosaic pattern differs between different winding angles. In order to have a good quality of the surface of the filament wound tube, we used a shrink tape. It also helps to remove the excessive resin, which is also better during the testing, and also the fiber volume of the composite is higher. In the axial compression testing, we had to use additional hand laminated reinforcement on the ends of the specimens in order to avoid a crushing in that area and the premature failure of the specimen. On the left side, you can see the experimental setup, which consisted of the mechanical instrumentation, and we also used acoustic emission technique in order to gain some additional information about the different acoustic events in the specimen while the specimen was crushing. And we use a spherical platen in order to better adjust the mounting of the specimen in the testing machine. And the acoustic sensors, we used 2 per specimen. We thought that it might be possible to locate the source of the acoustic event, but unfortunately in this kind of specimens we were not able to locate the events. We gained the information about the event without the location. So at first I would like to show you the results for the 45 degrees of the angle, the winding angle, and in this graph you can see the different load displacement curves for each pattern. And additionally, with the acoustic emission RMS signal, which is one of the most popular acoustic parameter used in acoustic emission technique. And what we can see on the graphs on the bottom of the slide is that when when a damage occurs in the in a specimen, the RMS is going up and the signals is higher. So we can see that for the exemplary in here curves, that in the case of 45 degrees, the signal were very low up to the maximum force when we had a huge rise of signals, so a huge amount of events occurred. So the different cracking, different failure modes occurred also. In the second configuration, 45 degrees of filament of winding angle and 2x1 mosaic pattern, there was the tendency was pretty similar, but for the most complicated mosaic pattern, 3x1, where the interlaces were more frequent, we see that there are a few cascades before the maximum force, which might show that the failure was also before the maximum force. To compare those mosaic patterns, we've calculated the compressive strength and the corrected absorbed energy. Corrected, it means that we took into account the differences between the thicknesses and the geometric differences between the samples, which of course occurs because of the technology, filament winding technology. And we can see that there is a correlation between the the number of mosaic pattern and the corrected absorbed energy, and with the rising mosaic pattern, the corrected absorbed energy is higher. A similar tendency might be seen in the compressive strength, but without such a huge difference. A similar result will be shown for the 55 degrees winding angle, and also the load displacement curves are shown, and which is more interesting, the curves with the acoustic emission signals, which are pretty similar to the tendency of 45 degrees. And to compare those different mosaic patterns, we didn't actually see a huge differences, statistically significant differences between the compressive strength for the compressive strength and absorbed energy between the mosaic patterns for this winding mosaic pattern. And the last group of specimens is 75, in which we also produced 3 different mosaic patterns. In this case, a lot of signals, a lot of acoustic emission signals occurred before the final failure for 2x1 and 3x1 mosaic patterns. And in this case, we might see the tendency of in compressive strength, which for the 3x1, so the most complicated, the most developed mosaic pattern, where the number of interlaces is the highest, we can see that the compressive strength was the highest, while the corrected absorbed energy didn't show any significant difference, mainly due to the scatter of the results. So to conclude, 9 configurations of composite fiber reinforced plastic filament wound tubes were tested in axial compression loading. And we've seen that the mosaic pattern influences the mechanical response of the tubes, both in terms of compressive strength and strain energy accumulation, depending, of course, on the winding angle. In the acoustic method, which we used, acoustic emission method, which we used, showed us the differences between the patterns, but it is planned in the future work to better understand these signals in this kind of tubes and try to correlate the signals, the parameters of the signals with the observed damages in the filament wound tubes during axial loading. Thank you very much for your attention. That's